hardware configuration that used an embedded NoisII. And what I want to do today is to talk about the software that's going to run on the NoisII that you're going to build. And there's a whole bunch of different topics that all go together to make it possible to program this. I found it useful to read the NIOS introduction. These are all linked up in Lab 4, plus a whole bunch of other stuff. The Altera monitor system. The NIOS software handbook. But what was absolutely essential, and you cannot live without, is the Embedded Peripheral User's Guide. Embedded Peripheral User's Guide. This has all of the details about timer layouts, parallel I/O port layouts, SPI connection, UART, and what every bit in every register means. So when you're trying to define a timer and turn on a timer and set up an interrupt on the timer, for instance, this is the book you need to read. You don't need to read all of it. It's, I don't know, 300 pages long. But you do have to read the sections that are relevant to the peripherals you are using, which is probably going to be, at minimum, a parallel I/O port. There's at least 3 different levels at which you can address or deal with I/O requirements in NIOS systems. There is raw registers, and I tend to use something, a variant on raw registers, because it's simple and straightforward. There are a set of macros which drive the raw register display description. There's also another layer called the hardware abstraction layer, HAL layer. And what I usually end up doing is some combination of all of these. I use the HAL for some functions, and macro to raw registers for some functions, and just bit blast other registers for other functions. And I'm not sure why, except it seemed to be the order in which I learned things. So you're not required to do it in any particular way. Whatever style works for you works. There are several places you can find out information about the system you just built. When you run the SOPC builder and click the Generate button, of course it generates Verilog, which builds your system, but another file, system.h, is also generated, which has a complete description of the system in a sort of human readable form. All the information is there. It's kind of terse, but you can find out things like the base address of the timer, the device name of the UART, various things which are critical for making your system work. System.h file will be someplace in the folder or a subfolder of the project that you are building, and you can search for it. It's faster than looking for it by hand. So you're going to want to, almost every time you build a new system, you're going to want to look at the system.h file to find out various things about where SOPC Builder put your peripherals. You're also going to want to look at io.h. That is in an obscure location, which took me a while to find. C Altera 11.0, or whatever the version number is that we're using in the lab. I think it's 11.0. Altera SOPC underscore builder underscore IP. And io.h has two critical routines in it that you can use. One is IO read, and the other is IO write. IO read takes as parameters a base address and an offset. I'll explain what those are in just a minute. And IO write takes a base address, an offset, and a value. The base address is assigned by SOPC Builder, and you can read it in SOPC Builder, but you shouldn't. Okay, you should get this, you should use a symbolic version, which is in system.h. So system.h is going to supply the base address. The offset for a given register means the following. For instance, a timer block has a base address. The first word is the status, and the second word is control, and the third words are some period stuff. So this is an offset 0 within the block. This is the base address. This would be offset 1 and offset 2 and so on. So we specify the base from system.h, the offset from Embedded Peripheral Users Guide, EPUG, the EPUG, and the value, of course, is going to depend upon what is being defined in these fields. For instance, for a timer, the first 3 bits, the control bits, are start, continuous, and interrupt enable. So this is bit 0, 1, and 2. And those definitions you would also get from the Embedded Peripheral Users Guide. Now, realistically, the way everybody learns to program is you find a program that works and you copy it. And then you start hacking on it until you've turned it into, you've morphed it until it becomes the program you want. And so that's how I learned to program this system. And you might want to use the examples I put up online to try and simplify your learning of this stuff. But You can go up one level. If you look at Altera underscore Avalon underscore PIO underscore regza.h, you will find macros that define how to get to all of the parallel I/O ports, all of the parallel I/O port status, or all the parallel the parallel I/O port register block. Or if you look up Altera Avalon timer reg.h, you'll find a set of macros that packages up the I/O read and the I/O write at a slightly higher level for perhaps more ease of use. I'm not sure it's easier to use. These are also in this SOP C builder underscore IP directory. There's also another file that I found essential, and that was alt irq.h. These are register level, but this is a HAL level header file. I found dealing with the interrupts at the HAL level was easier. But you may need to look at that header file also. So there's a fair amount of reading here. There's a and you can do it by the just-in-time method, which is to say you program until you can't program anymore and then you read. But it might be more efficient to at least read some of the introductions to the embedded peripherals user guide before you try and start programming. As an example of what's in system.h, again, this is generated by SOP C builder for your viewing delight. There are a bunch of defines in here, including define. Now, let me just step back and say that in SOP C builder, I asked for a parallel I/O port, PIO port, of whose name is switch. What is in system.h is define alt module class underscore switch. Aha, that name appears. Mumble. It's over there, and it's of type Altera Avalon PIO. And there's another define, which is switch base, which takes on the value, in this case, 0x810. So, what SOP C builder did, for reasons only it understands, is to take this lowercase version, uppercase it, and append underscore base. And then assign an I/O address to it. When you specify the base in a read or write, you could use 0x810. That would be a bad idea, because every time you run SOPC Builder, it feels free to change the addresses. Don't do that. Use switch base. That is the symbolic name that corresponds to the absolute address. You can use the absolute address at your own risk, but why not use the symbolic equivalent and save yourself tears trying to debug when what's wrong is you're no longer actually writing to the I/O port. And there's, maybe 15 other defines. Define switch bit clearing edge register 0. Define switch capture 0. Data width 8. Oh, that's actually useful. This is an 8-bit port. Is there an interrupt associated with it? What's the interrupt controller ID? And the switch name. Oh, define switch name. Just define switch name as quote slash dev slash switch. And some of you may recognize that that's a very Unix-like thing to do. So, use the symbolic addresses if you're going to use direct I/O reads and I/O writes. So with that preamble, are there any questions? You have to sort of look around for this stuff, but the Windows search facility will help you plow through the header files. So let's write some code. So then now I'm writing code specifically for the CPU that we talked about on Friday that has an LCD driver, it has SD-RAM, it has LEDs and switches attached, as well as a 32-bit output for direct digital synthesis control, and a timer, which is what we laid out on Friday. So we're going to start out with the usual C kind of includes. We're going to have to include, of course, system.h before we do anything else, because that's got all of the definitions of all of the symbols that define the computer you just built. And we're going to do an include. And I'm including this because I'm going to use printf. We're going to include standard I/O. Oh, by the way, yes, the quotes mean look locally. The pointy brackets mean look wherever you're supposed to look. I don't know how it resolves that. Then, because we're going to use interrupts, we need to include sys/alt irq.h. And then, because I used the kind of intermediate level I/O macros in this example, I had to include Altera Avalon timer reg.h and include Altera Avalon PIO reg.h. These names are astonishingly wordy, as you will see. Not only the name of the header file is wordy, but the actual macros are like 25 character long names. I think if I was going to use these for more than an example, I would redefine them as something shorter. Or just use IORD or IOWR. And some of you who have seen my coding style before will undoubtedly feel a flash of revulsion when you see this. I like to define the word begin as open bracket and define end as close bracket. And the reason I do that is not because I want to make C look more like Verilog. It's because I can't tell the difference between curly brackets and round brackets because there's only 2 pixels difference. And unless you give me a 14-point font, I can't tell the difference. So I prefer to use the whole word. And now here's some obscure stuff. This is the device driver that by default runs the LCD, emulates a terminal program, call it PuTTY, whatever, which emulates a VT100 terminal, which was invented by Digital Electronics Corporation in the 1970s. The VT100 was a text-only terminal that people found they wanted to use for as if it were a window. So it was a sequential writing terminal, upper left to lower right, but they retrofitted cursor controls so that you could move the cursor around and do various things like insert characters in the middle of the screen and erase the whole screen or start writing in the middle of the screen. So there's a set of very weird commands that were originally defined for this hardware device. It was a hardware device. It was a terminal you set on your desk. It was bigger than a modern computer, and all it did was have a serial pair of wires that went off to the actual computer. But it became a standard, an ANSI standard. And so the escape codes got ported to terminal emulators, which got ported to the device library. So when you write to the LCD, you can use VT100 escape codes. And we're going to define escape top left. This takes the cursor to the top left corner of the logical screen, whatever it happens to be, is the string square bracket 1 semicolon 0 capital H. Wow, jumps out at me. And there's a few other things like that. Let's define a couple of more just for grins. LCD clear is the same as the old screen clear, which is 2J, or square bracket 2J. And we need, there's a couple of more we're going to use, but I'm not going to write them out. And we also need a static unsigned character ESC, which will be the escape character, which is 0x1b. That's the really low-level, grody stuff. Now remember, let me remind you what this program does. I think I said it on Friday. What this program is going to do is to count from 0 to 8, and in the process put out one of 9 notes from C, middle C through C above middle C, while blinking an LED to tell you which note it's putting out. So we need to open up a file descriptor for the LCD because the I/O is file oriented like Unix. So we have to open up we have to define a variable of type pointer to LCD file descriptor. And now we can do this in various orders, but let's write the interrupt service routine for the timer. And we need a timer here because we want each note to last 1 second. So we're gonna play middle C and then D and then E and go on up, and we want each note to last 1 second, so we need an interrupt routine to time out 1 second. And of course, if this is an interrupt service routine, it must be of type void, right? Because interrupts cannot return a parameter because there's no place to return to. All right. So we cannot return a parameter. However, there is a context variable which we can use to communicate between main and the interrupt, but do not consider it a parameter. It's more like a global. And then we need a variable. We need an address which tells us where the interrupt is, except we better put a name on here. We'll just call this timer ISR. It is written as if it's a function. And the way it becomes an interrupt service routine is in main, you have to identify to the interrupt handler the name of the function which is to become the interrupt. I can use my nicely defined begin and end. And I'm going to define a volatile, which is going to be a pointer to int of flag pointer, and we're going to make this equal to, and why did I do this? I don't even remember why I did this, but I think it was because I'd already used the variable in a different way. Now, the very first thing we have to do, the very first executable code we do in an interrupt service routine is to reset the interrupt flag which caused the interrupt service routine to fire, because the microcontroller does not do that automatically. And if you don't reset the flag, as soon as you exit the interrupt service routine, it'll take another interrupt. So we can write this in one of two ways. Using the definitions from Altera Avalon timer regs underscore .h, we have IOWR Altera Avalon timer status, STAT, status timer 0 base 0. Or we could just write instead IOWR timer 0 base offset 0 value 0. Which one would you write? So timer 0 base, this is the offset, this is the value. The only thing that this 20 character name gives you is that it looks up for you the offset to the status register. Then we're going to increment the memory pointed to by flag pointer. And then if flag pointer is equal to 9, we set flag pointer back to 0. And then we end the interrupt service routine. So this is just going to count from 0 to 8 and then start over again at whatever rate we set the timer to, which we will do in main. Any questions? And like every other microcontroller that you've ever had to deal with, most of the complexity is in trying to figure out the I/O library, because the rest of it's just generic C. Now, for reasons that escape me, main returns an int. Where does it return it to? I don't know. There's no operating system. But that's the definition. And we're going to define a volatile int, which is flag. And I should emphasize that any variable which is shared between an interrupt and main has to be declared volatile. The reason is the compiler is very good at optimizing away variables that never change. Flag is never going to be modified. It's going to be read but never modified in main. The optimizer will look at that and say, value is always 0. Don't need that variable. unless you make it a volatile, which signals to the compiler that some other process can asynchronously modify this variable. And we want an unsigned int, which will be switches. We'll use that to read in the switches from the DE2. And then we need an unsigned int array of notes, which are going to have the value 262, 294, 330, and so on, up to 523, and then 0. And the 0 here causes the direct digital synthesis unit to increment 0 times a second, which means it produces DC, which you can't hear, so that's a rest. Set flag equal to 0. Now the very first thing we need to do is set up the timer. Turn on the interrupts so that everything starts to tick. And I'll use the short form. The long form is IO write Altera Avalon timer period low, or we could just write IO write timer 0 base. The offset for the low period is 2. And oh, why do we have low and high? Wait a minute. It's a 32-bit timer. This is a 32-bit bus. Why do we have to have a low and a high word? Because the timer was originally defined for a 16-bit version of the microcontroller, and they didn't modify it. And so you have to load the low 16 bits separately from the high 16 bits. So this is the low 16 bits, which we're going to set to 0x7840, and this comes by dividing. I wanted a half-second period here, and 25E6, 25 times 10 to the 6 counts, turned out to be hexadecimal 17D7840. So that's the low 4 bits, low 16 bits. And we're going to do an IO write timer 0 base 3 0x17D. That sets the timer to 1 second. Half second, excuse me, half second. Now we have to turn it on. And for that, I'll just use the long form for variance here. IO write Altera Avalon timer control timer 0 base 7. 7 here means set the low 3 bits, which correspond to start the timer, make it continuous so that as soon as it hits 0, it reloads the starting value and starts over. So we get a continuous half-second time base, and bit 0 is turns on the interrupt. So it allows the system to interrupt on timer equals 0. This is a down counter. So it starts at the loaded value, counts to 0, throws an interrupt, resets itself since I've specified continuous mode, and starts again. The usual periodic timer. Then we're going to register this interrupt with the interrupt handler by doing an Alt IRQ register. Timer 0, timer underscore 0 underscore IRQ. That's another symbol that comes out of system.h. This symbol comes out of system.h. It's an interrupt number. We need to pass it a void pointer to flag, and we need to give it the name of the function that we wrote. Flag. What is it? Void pointer to flag. Yes. It is an address.
No, I mean flag is an integer, right? Shouldn't it be converted to a pointer to be updated?
That's the pointer to it. All right. I got to tell you though, I'm not very good at pointer arithmetic, because I'm a recycled Fortran programmer where there's no pointers.
But this is C, right?
This is C, yes?
Then you would have to pass ampersand of flag, right, to pass the address of flag. This is a variable, right, which is being passed. Just typecasting it to white star.
I'm typecasting it to a, yes.
I think you would need ampersand.
I think I don't. Because this works.
Oh, okay.
And then we have to define the device file, the file name, the file descriptor for the LCD is fopen. We use an fopen. Fopen acts as if it's a Unix file open, but there is no Unix operating system. So we give it a device /dev/lcd, and we're going to open it for write, so we have to specify that. And to be on the safe side, we better check and make sure that actually worked. If lcd fd is equal to null, then the open failed, and we should do a printf unable to open LCD \n. Printf by default will go to the console. I specified a JTAG UART, so it'll go to the JTAG UART. And at this point now, we can fault. I don't have quite time to do this. At this point, the next step is to fall into the usual endless loop, which is going to do nothing but wait for the interrupt. But I will do that next time. Are there any questions about Lab 3? the current lab. So how many people got noise, have drum-like sound coming out of their simulators at this point? Yes, yes. How many people have a ear-rending screech coming out? All right, good. Okay, honesty is good. Yeah. And do you have a question you want to ask about generate blocks? Okay, so a generate generates hardware. It is not an iterative structure. You cannot ever instantiate a module in an always block, because that implies that you're going to instantiate hardware. What does it mean? It means you're going to instantiate hardware on every cycle. You have to instantiate hardware outside of a block. It cannot be used for iteration. Generate blocks should not be considered do loops. They should not be for and X loops. They should not be considered iterative structures. They are a way of building hardware only. You can nest them, yes. It's kind of like, it's a very weird little piece of procedural code that is only executed, that only exists at compile time. So it's like a directive to the compiler to make lots of copies. But once the compile is done, there is no iterative structure left. Any other questions about Lab 3? Anything else? Loud screechy sounds can happen for a number of reasons. An SIGN error, sign error, on any one of the terms can cause the system to be unstable. If rho is greater than 1/2, the system will always be unstable. If rho is equal to 1/2 in whatever strange unit you happen to be using, it'll be unstable. So make sure that you're in terms of the bit, in terms of the arithmetic system you're using, that rho is less than 1/2. One way to see if it's a stability problem is to turn up the damping. If you're marginal stability and you turn up the damping, the system should become stable. Anything else? Lab 3. Any questions on the C so far, aside from the pointer, which I'll get back to? I'll have to go think about that for a while. Okay, have a good week, guys.